Hey, welcome back everybody. In our last couple of videos, we talked about what a sequence was, and then we saw what the definition of convergence of a sequence was. And that was a long, complicated sort of a definition. The idea is simple that, if a sequence is going to converge, the terms of the sequence should get very, very close to the limit as you go out through the sequence. They should get closer and closer and closer to what they converge to. Of course, how do you say that rigorously, right? What does that mean to be getting closer and closer and closer? So what that really means, of course, is if you tell me how close you want to get, then you should be able to get that close and stay there throughout the rest of eternity, right? And if you get closer, or if you want to get closer, then you can go further out in the sequence, and from that point on, stay inside that little error band that we were drawing. We used epsilon as sort of the size of that error band, how close we were wanting to get to the limit. So that was a definition of what it means for a sequence to converge, and we saw some examples of why a sequence should converge. We played with the sequence 1 over n, and saw that had to be converging to 0. But now what we want to do is write out a nice, formal, rigorous proof that a sequence converges. Okay, well, what would this kind of rigorous proof that something converges look like? Well, if we remember our definition, it looks like all those pieces there on the screen. So, because of the way the definition is structured, a typical proof is going to have three parts. So, the first thing we have to deal with is that for every epsilon at the very beginning. So, if we remember back to what we were talking about at the very beginning of this course, when we talked about logic and quantifiers and all of that, when we're writing a proof that starts out for every epsilon, it means that we need to assume that we have an epsilon, but we leave it as a letter, right? We don't claim that it's a particular number, like we did in those examples that we were doing at the very end of the last video. When we write a real proof, we leave epsilon as a letter, and we carry that all the way through the rest of the proof. We don't assume that there's anything special about it. That way, it'll work no matter what epsilon is. Second thing in the definition is this statement about there exists a capital N. So we have to prove that there is a capital N that does something. So how do you prove a there exists statement? Well, one way to do it, and the typical way we will do these proofs, especially in this video, we're going to do a constructive existence proof. So if you remember when we talked about how to prove there exists something, you could do it constructively, which means you show that there exists an N by telling me what it is. There's another way to do it too, where you could do a non-constructive proof by proving that one has to exist without telling me what it is. But for these kind of proofs, it's much easier to just tell you. In fact, the vast majority of the work goes into figuring out what the capital N should be. The last part, that's an implication, right? It's a P implies Q kind of statement. And we're going to do this with a direct proof. So if you remember back to all the different kinds of proofs we talked about, this is a P implies Q kind of statement. So a direct proof of that would be we just assume P is true and then show that Q has to be true. Okay? So that's the structure of what these are going to look like. And we will circle these various parts as we go through the, uh, the rest of this lecture. So here's a nice formal rigorous proof that 1 over n converges to 0. So first step is we need to deal with that universal for every epsilon part. So I'm going to fix an epsilon greater than 0. Okay, why the word fix? It could be anything. It could be suppose that epsilon is greater than 0. It could be let epsilon be greater than 0. I like fix because, well, mathematicians tend to fall into habits and they tend to say fix an epsilon greater than 0. So you look at lots and lots of books, and lots of mathematicians will start this by saying fix an epsilon. They don't mean that the epsilon was broken. What they mean is that you're affixing a particular one. It's like I've got one in my hand, right? I've like we would say, you fixed this to the wall, right? It means that I've got a particular one, right? Although I'm going to leave it again as a letter so that it could represent anything. I'm not assuming anything special about this epsilon other than the fact that it's positive. Next, I'm going to say go grab any capital N you want to, so long as it's a positive integer and so that it's greater than 1 over epsilon. So here's my there exists part. Now this is maybe worded a little strangely because I just told you to go choose your own N. Well, kind of. I told you to choose any n you wanted to bigger than 1 over epsilon. So any n that's bigger than 1 over epsilon will work, so I don't really care which one it is. Um, this is typically how people will word these sorts of things, but I'm dancing around one issue here, which is suppose that epsilon were some weird decimal number, 1 over epsilon, then will be some strange decimal number like, 7.39462, and I need my capital N to be an index, right? A positive integer, because that tells me how far I can go in my sequence before I enter that green epsilon band and stay in there forever. So n should be a positive integer. Um, Again, sort of telling me how far out to go in my sequence. So this is why I say just pick any positive integer you want to, so long as it's bigger than that 1 over epsilon. And again, 1 over epsilon may be some weird decimal number. And so you could say pick the next biggest integer. That'd be fine too. But people usually don't. They just say just grab any integer you want to, so long as it's bigger than 1 over epsilon. Now for the next part, again, this is a direct proof. So we're trying to show that P implies Q, right? Some implication. And when we do that, we're going to assume the P and show that that implies Q. So the P part was that little n was greater than or equal to capital N. Okay? The Q part, and I'm going to have to do some algebra and stuff to show that the Q part is true. And so here's all the algebra that does that. Now this is really odd looking, and maybe we'll talk about this for just a second, but we'll see where all of this comes from over the next few minutes. For right now, maybe it's worth just looking at it and noticing that we're trying to show Q, which from the definition, that was that the distance between 1 over n and 0 was less than epsilon. So we started out with the absolute value of 1 over n minus 0, right? That's what we need to show is less than epsilon. Now, of course, subtracting 0 doesn't change anything. 1 over n is positive, so that's fine. I can just, in the next step, say that that's the same as 1 over n. Now, here's where I use the p part, right? I'm assuming that little n is bigger than or equal to capital N. Now, remember the way that things work if you start working with denominators. And it'll be really important to keep in mind as we go through this. When you want to make something larger, right, you can do that by making the denominator smaller. So when I go from 1 over little n to 1 over capital N, right, then that should get bigger. Right? And so how do I make sure that that happens? Well, I'm assuming, if this is the p part, that little n is larger than, bigger than or equal to, capital N. So when I go from 1 over little n to 1 over capital N, I've made the denominator smaller, right? Because again, little n was bigger than capital N. So when I replace that little n with a capital N, I've made the denominator smaller, which makes the entire fraction larger. So perfect. That's how I get to replacing all my little n's with one particular number, capital N. That's the key there. Once we get to that point, then we're fine, because now I know stuff about capital N. It was picked to be bigger than 1 over epsilon. So the next step, I replace 1 over capital N with this number 1 over epsilon, which again, 1 over epsilon is smaller than capital N. And when I make the denominator smaller, I've made the entire fraction bigger. So this next step takes me from 1 over capital N to 1 over epsilon. And of course, I can simplify that, right? 1 over epsilon, that just flips and you just get epsilon at the end. And there's my Q, right? The distance between 1 over n and 0 is less than a whole bunch of stuff, less than, and finally we get to epsilon. So all of that, right, is a proof of the implication part, right? That if n is bigger than or equal to capital N, then the distance from Sn to 0 is less than epsilon. So finally, all those three pieces together proves that 1 over n converges to 0. All right. Maybe it's a good idea to stop at this point because you're about to go and work on homework and write your own proofs. And so the most important thing to remember as you start writing your own proofs and doing your homework is this. You have to work out everything on scratch paper before you try to write it up nicely. Okay, this often just blows people's minds. I mean, this is so different than they've ever done in any of their math classes until now. that it's worth really making a big deal out of. And so stop the whole process and let's talk about this for a second. When you work a calculus problem or an algebra problem, right? You write down the problem, you do a whole bunch of stuff, blah, 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 blah. You get to the end, the answer is 42, you circle it, and there we're done. That's the way you do homework in every other math class you've had up until now. But with these kinds of proofs, okay, it's not going to work that way. Right? I mean, you might think that it will, because when you look at proofs in the textbook or watch what I just did in the video lectures, what you're going to see is this nice polished version of the proof after I've done all the horrible gross work to figure everything out. I mean, in that last proof, where did that 1 over epsilon come from for capital N? How did I just know to do that? Well, the answer is I had already done all the icky work of figuring that out ahead of time. And I did that on scratch paper and I didn't show that to you. Right? So when you do your proofs, um, to turn in for your homework, then the first step is to sit down on a piece of scratch paper or back of an envelope, something that you're not necessarily going to turn in, and figure out what your capital N has to be and do that kind of calculation stuff. Then once you know what it looks like, then you can write this sort of nice polished proof. Oh, well, obviously, capital N needed to have been blah, 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 and we just do it. So let's show you how that last proof came about. Okay, what would the scratch work look like? What did I do in order to figure out how to do the proof that I showed you a second ago? Well, I knew that I was going to eventually need to get 1 over n minus 0, and take the absolute value, less than epsilon. Right? And that would happen, of course, whenever little n was bigger than or equal to this magical capital N. But what is this capital N? That's the whole point, right? I've got to show that this capital N exists. I need it to be the right thing to make the implication be true. So here's what I'm going to do. I just start writing out 1 over n minus 0, take the absolute value of that, and see what I can do with it. Right? So eventually I'm going to need to show that that's less than epsilon. But you remember from the original proof, there were some steps in between. Right? So, I mean, first thing I can do is 1 over n minus 0. Okay, subtracting the 0 doesn't change anything. And the 1 over n is positive. So let's just get rid of the 0 and the absolute values. Now what? Well, the only thing that I know about anything, right, is that little n is bigger than or equal to capital N. And so we can use this trick, right, that I'm going to need to take the absolute value of 1 over n minus 0 and get bigger and bigger and bigger and bigger and bigger. In fact, in some ways, all of analysis, and especially these kind of proofs, is really the study of less than. I needed to go less than, less than, less than, less than, maybe less than or equal to, less than, and eventually get epsilon. So what could I do here to get a less than or a less than or equal to? So in other words, how do I take 1 over n and get something bigger? Well, I could replace that little n in the denominator with a capital N. And when I do that, I've made the denominator smaller. Again, you might want to pause the video at this point and think really hard about this, because this is the absolute key to understanding how these proofs work. I've taken little n and replaced it with capital N. Right? And I'm assuming that little n is bigger than capital N. Or another way to say that is, I've gone from little n to capital N. I've gone from a number which was bigger to a number which was smaller, again, in the denominator, which makes the whole fraction get bigger. Again, it's probably want to rewind that and listen to that again, because that's really weird, right? I'm making the denominator smaller using an inequality that looks like there's some biggerness happening, because we wrote the inequality as little n is greater than or equal to capital N. But another way of saying that is capital N is less than or equal to little n. I made that when I go from 1 over little n to 1 over capital N, I make the denominator smaller, which makes the entire fraction bigger, or bigger than or equal to. Right? And so, great. So how do I do something with that now, right? Because the cool thing is I've dealt with the infinitely many little n's that I could have, and now I've sort of reduced everything down to this expression that just involves one particular capital N, right? So now if I just choose my capital N wisely, I can make that guy be less than epsilon, right? I don't have to worry about every possible little n. I just have to worry about this one particular capital N. So how do I get that to be less than epsilon? Okay, so again, this is more scratch work. I need 1 over capital N to be less than epsilon. All right, so let's figure out what that means for capital N. Um, there's other ways to solve this inequality and play with it, but for now, maybe let's multiply through by capital N. That would give me 1 is less than epsilon times capital N. Then I could divide by epsilon. I don't like that, right? Because that says 1 over epsilon is less than capital N. That's not how I usually think, right? I usually think with it written the other direction. So 1 over n is less than capital N is of course exactly the same as saying capital N is bigger than 1 over epsilon. And that's usually how we think about it. And that's perfect. That's exactly what I need. Now I know what I have what kind of capital N I'm going to need in order to make this guy work. I just need to have a capital N that'll be bigger than 1 over epsilon. As long as that's true, then my P implies Q part will work when I start writing it up nicely. So I've circled it there even from the scratch work to make it obvious that that was the whole point. So I figured out what my capital N needs to be. So now I go write my nice fancy looking proof that I'm nice and polished and ready to be turned in for homework. So I start out by fixing my epsilon greater than 0. That takes care of the for every epsilon part, right? I'm leaving epsilon as a letter because I'm doing a universal quantifier proof. The next step, I need to show that a capital N exists, and so you just take one that's an integer and bigger than 1 over epsilon. Okay? So you get to pick. The person doing the reading gets to pick which one they like, but I'm showing that one exists by obviously there is a capital N bigger than 1 over epsilon. That's an integer. Grab that one. Now the next part is a direct proof, right? That whenever little n is greater than or equal to capital N, that the distance between 1 over n and 0 is less than epsilon. So I'm going to start out by assuming the p part, that little n is greater than or equal to capital N, and then I write out, all of this long string of stuff. But this works because of the scratch work I just did. So what I have written here is that the absolute value of 1 over n minus 0, well, of course, if I subtract 0 and then notice that everything's positive, so I don't really need the absolute values anymore, then I get just 1 over n. Because of what I'm assuming in the first part of the implication, that little n is greater than or equal to capital N, then 1 over little n is less than 1 over capital N. Now if I again replace capital N with 1 over epsilon, again I've made the denominator smaller, so it makes the entire fraction bigger. And now, oh look, 1 over epsilon, that's just epsilon. So that was the Q statement. So all of that proves my implication. Right? So we're done. There's my proof that 1 over n converges to 0. All right, this desperately needs another example. Let's try something like 1 over square root of n plus 3. Now, of course, if we think about this for a second, it's obvious that this should converge to 0 because there's an n in the denominator, which is getting larger and larger and larger, and there's a 1 in the numerator, which is just staying 1. So this sequence will clearly converge to 0. But how do we prove it? Well, let's do some scratch work to see. So I'm going to need to play with the absolute value of 1 over my square root of n plus 3, that's my sequence, minus what it should be converging to, the 0. And of course, well, same sort of thing happens before, right? Subtracting 0 didn't really change anything, and the absolute value is even, of all this is still positive, so I don't even really need that. Now, notice that I've highlighted the plus 3 there. The thing is, if you just dropped the plus 3, the whole fraction will get bigger. Because remember our rule, if you make the denominator smaller, it makes the whole fraction bigger. And that's what I need to do. I need to go less than, less than, less than, less than, right? So how do I fix this? I ignore the plus 3. Because if I'm not adding 3 in the denominator, then of course, just the square root of n by itself would be 3 less than it would be if I had added the plus 3. So getting rid of the 3 made the denominator smaller, which makes the entire fraction bigger. And of course, now I can play that game I did with the little n and the capital N. If I replace that little n with capital N, then again I get a fraction that's bigger. The The whole fraction got bigger. And now notice I've done exactly what I wanted to do. I've taken the sequence that depended on little n, where little n could be, all infinitely many possible numbers, and I've gotten a bound on it that just depends on capital N. And that's the key. So far what I've shown is that whenever little n is bigger than or equal to capital N, which that's the p part of what we're trying to prove, then I can get my absolute value of the sequence minus 0 to be less than 1 over square root of capital N. I need that to be less than epsilon. That's easy enough, right? I can drop the absolute values there because 1 over square root of n is positive. And how do I do this part? Well, again, I've got my scratch paper. 1 over square root of n less than epsilon. Let's figure out what the n has to be. Now, I could multiply through by square root of n. I did that in the last example. But just to show you a different way to think about this that I think is a little quicker, let's flip both sides. In other words, I got 1 over n on the left, I got epsilon on the right. What would happen if I flipped that? Right? So on the left, I just have square root of n now, and on the right, I get 1 over epsilon. When you flip a fraction, it changes the inequality around, right? It's easy to think about it if you think of some numbers. So 2 is less than 3, but if you flip it, a half is more than a third, right? So the inequality has to flip. So by flipping the inequality this way and flipping the fraction and then flipping the inequality, it lets me put the n on the left hand side the way I like it. So now if I just square both sides, I get that n should be bigger than 1 over epsilon squared. Again, you can do the actual algebra here however you like. But the point is, if I pick a capital N bigger than 1 over epsilon squared, that ought to work. That's what we went through all this scratch work to figure out. There's my capital N. Now I don't necessarily turn all that in, right? It's not going to be what I do when I write up my proof. You're not going to see all of this screen. What you're going to see, or what I should see on your homework paper, is a proof that looks like this. First we fix our epsilon. Again, that's the for every epsilon universal quantifier part of the proof. Then we say we choose some positive integer n, capital N, so that the capital N is bigger than 1 over epsilon squared. That's the existence of the capital N part. I've got my capital N right there. It's an integer bigger than 1 over epsilon squared. Now we do the proof of the implication. When little n is bigger than or equal to capital N, then here we go. The distance between my sequence and 0, right? Well, if I just drop that 3 in the denominator, it makes the whole fraction bigger. If I replace that little n with a capital N, it makes the whole fraction bigger. If I replace that capital N with 1 over epsilon squared, it makes the whole fraction bigger. And now, of course, I've got 1 over epsilon squared inside of a square root. When you take the square root, that makes it 1 over epsilon in the denominator, which flips and just simplifies to being plus epsilon. And so there we go. There's my proof of the implication part. And so I have that my original sequence converges to 0. The same 3 steps. Okay, let's try another example. This one looks a lot like the last one, only there's a minus in the denominator. It's going to cause us a little trouble. So try the scratch work. If I start out by writing my absolute value of the sequence minus 0, because of course obviously the sequence is going to converge to 0. Not all of them do, of course. We'll see an example in a second that doesn't converge to 0, but of course this one does. Now, the first thing I can do is subtract off the 0, right? Get rid of it. And now you notice that I've got in the denominator a 5n cubed minus 3n. And I've highlighted the minus 3n because, see, I can't just drop the minus 3n like we did last time. Because, again, if I did that, what would happen is the inequality would go the wrong way. See, I need to be making the denominator smaller every time in order to make the whole fraction bigger. And if I don't subtract something, right, that doesn't make it smaller, right? In other words, right now my 5n cubed is having 3n subtracted from it. Okay, if I don't subtract that 3n, then I've made the denominator larger. Oh, that's bad. That would make the whole fraction smaller. You see from the screen there what's going to happen. So we don't just drop the negative 3n, right? How do we get out of this conundrum? Well, the trick is we just subtract more. right? Rather than subtracting, you know, 3n, let's subtract even more. Let's subtract 3n cubed. Right? That would be even more than we had before. Okay? That's really cool because now, of course, the algebra comes to our rescue here, right? I get in the denominator 2n cubed. See, there's a lot of room between 5n cubed and 3n. So I could just subtract some more. And the trick is to subtract so much more that I subtract off something cubed. Now I can combine the like terms, and it's now nice and simple and easy to deal with. So I've taken that entire denominator where I had two terms, turned it into just one. So again, to recap what we have here, right? If little n is greater than or equal to capital N, then we start out with absolute value of my sequence minus 0. And we can ignore the 0, of course, because subtracting 0 doesn't do any good. And now our trick was to replace that minus 3n by minus 3n cubed so that we're subtracting even more. Now we combine like terms in the denominator. That just gives me 2n cubed in the denominator. That's perfect because now that I've got down to just one term in the denominator, I can replace all those little n's with capital N's and make the entire fraction bigger. So this entire thing becomes less than 1 over 2 capital N cubed. And of course, I can drop absolute values there because now everything's positive. I need that to all be less than epsilon, which means I need that 2 capital N cubed to be less than epsilon. So now we just get in our scratch work, we figure out what we need for the capital N, and I can, well, my favorite trick is just to flip both sides here, right? So to make that 2 capital N cubed should be bigger than 1 over epsilon. And then if I divide both sides by 2 and take the cube root, capital N should be bigger than 1 over 2 epsilon, and then take the cube root of that. So again, this looks like magic, right? And it will if you just see what I'm going to show you in just a second. When I write up the proofs all nice and neat and fancy, where in the world did this cube root and the 2 epsilon? How did you figure all that out? Well, of course, I figured it all out before I started writing any of the proof down, right? I did all of this in the scratch work. So now when we write our fancy final proof, it will look nice and neat, right? First, we fix our epsilon greater than 0. That's perfect, right? That takes care of the universal for every epsilon. Then I show you that there exists a capital N, right? I just need any integer that's bigger than 1 over 2 epsilon to the 1/3 power. Then the last part, I have to assume that little n is bigger than or equal to capital N and show that this all works. In other words, that the absolute value of my sequence minus 0, and then I start writing less than or equal to until I get to epsilon. So I can replace that minus 3 in the denominator with 3n cubed. Then that simplifies nicely to just give me 2n cubed. And I can replace that little n with a capital N, again, making the whole thing bigger or bigger than or equal to. And now because I know that my capital N was fixed, in particular capital N, so that it was bigger than 1 over 2 epsilon to the 1/3 power, I substitute that in the denominator. That makes the whole fraction bigger. And look what happens, right? I've got 1 over 2 epsilon to the 1/3 power. It's all being cubed, so that cancels that. The 2 cancels with the 1/2 there and leaves me a 1 over epsilon in the denominator, and all that untangles itself to just become an epsilon. And there we go. There's my proof of the implication part. So victory lap, right? I can say that my sequence converges to 0. That last statement about thus this sequence converges to 0 isn't strictly speaking necessary, but it is kind of cool to get to write that because it's sort of like saying, nah, 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 I got it proof and it's done. So, okay, here's another example. Here's one that doesn't converge to 0. So if we look at this for a second, you'll see that I've got 3n squared plus 4 over n squared plus 5n. So the most powerful thing in the top is the n squared. There's also an n squared in the bottom. That's the most powerful thing there. So it's really the 3 over 1 that determines what happens. So this thing's obviously going to converge to 3. So how do I prove that it converges to 3? Well, we start with the scratch work. We start out by saying the distance between our sequence and the limit, which is 3, right? That should be blah, 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 less than epsilon. So how do we get there? Well, This isn't like the last couple of examples because I can't just ignore the um, the limit because it was 0 before and now it's a 3. How do I deal with that? Well, the obvious thing to do here is get a common denominator and try to combine this and see what we've got. So what I'll need to do is multiply that 3 by, well, n squared plus 5n over n squared plus 5n to get a common denominator. When we do that, right, the denominator will be n squared plus 5n. Look what happens in the numerator. This is really cool. When I multiply that n squared plus 5n times the negative 3, I'll have a negative 3n squared. That will cancel the positive 3n squared that was already there. And my um, numerator will just be left with a negative 15n, again from multiplying the negative 3 times the 5n, and also the original plus 4. So this is great. They all should work like this because now notice what's left has a bigger power of n in the denominator. And that's what's going to make this thing be small. Okay, so what's important to deal with here is that plus 4 and the plus 5n, right? So I'll highlight those so we can figure out what we're going to do here. I need to write less than and then another step, or less than or equal to and another step. So how do I do that? Well, let's think about the plus 4 first. If I want to make that entire fraction bigger, I can make the denominator smaller, or I can make the numerator bigger. So how do I make the numerator bigger with that plus 4? If I just drop it, then that's not going to make it bigger. So the trick is to add more, right? That'll make it even more bigger. And so let's change that from being a 4 to a 4n, right? That's definitely going to be bigger. Instead of just adding 4, I'm going to be adding 4n. But that, of course, will let me combine terms to make this much simpler. Okay? On the other hand, if I were to look at this n squared plus 5n there, okay, what do I do with that? Well, maybe what I could do with that is just drop the plus 5n. Because if I just erase the plus 5n there, that would make the denominator smaller, which makes the entire fraction bigger. So my denominator just becomes n squared. The numerator I can combine the negative 15n and the 4n into like a negative 11n. And now the n and the n squareds cancel and the whole thing simplifies itself down to just negative 11 over n, which is awesome because at that point I'm assuming that little n is bigger than or equal to capital N. So if I replace my little n's with my one capital N that I've got, I'm good to go. Now I have taken all those little n's and they're not in my expression anymore. Right? I found something which is a bound on all of that that only depends on the capital N. Negative 11 over capital N, take the absolute value. Of course, I could at this point take the absolute value and change that negative 11 into a positive 11. And so let me get some more room to work here, and we can do that, right? So what we saw in the last screen was that whenever little n was bigger than or equal to capital N, then my sequence minus its limit, take the absolute value, do a whole bunch of work and simplification that got me down to being less than or equal to 11 over capital N. Now, again, I need that to be less than epsilon, so I just figure out how to make that work, right? What should the capital N be so that 11 over capital N is less than epsilon? Again, you could multiply through by the capital N, or if you want to do my flipping trick, flip both sides and change the inequality. So instead of 11 over n is less than epsilon, flip it so you get n over 11 is bigger than 1 over epsilon. Now multiply through by the 11 and you get n has to be bigger than 11 over epsilon. So there we go. We figured out what our capital N has to be. We're ready to write up our proof. So how's this going to go? Well, same way we always start things. We fix our epsilon, which will take care of that for every epsilon part of the definition. We tell you what the capital N has to be. That takes care of the there exists a capital N, right? As long as the capital N is an integer bigger than 11 over epsilon, this is going to be good to go. So for the implication part, I'm going to assume that little n is bigger than or equal to capital N, and then start doing a whole bunch of calculating. So this will take maybe more than one line to fit on the screen here, because first I need to take my sequence minus the limit, take the absolute values. Let's get a common denominator, just like we did in the scratch work. And when we simplify that, we have negative 15n plus 4 over n squared plus 5n, and we got the absolute value of all that. Now, what makes this work really cool, just exactly what we did in the scratch work, we can drop the 5n in the denominator and replace the 4 in the numerator with 4n. All of that will make the whole fraction bigger. Well, that simplifies down to just negative 11 over a little n, and now we replace the little n with a capital N. Now we replace the capital N with 11 over epsilon, all of which makes this bigger, and again, taking the absolute value to get rid of the negative sign, we end up with just an epsilon, which is perfect. There's my implication part. Again, this was longer and uglier than the first few we saw because doing all the algebra took longer. But see, you don't actually do the algebra here when you're writing up your proof. You do that in the scratch work to figure out how all that's going to work. When you get to this point, we're just writing it all down.